The dream of unlimited energy. Hey everyone, and welcome back to Sciencepect. Imagine a power source that could provide clean, virtually unlimited energy, forever changing our world and solving global energy needs without the harmful emissions of fossil fuels or the long-term waste concerns of traditional nuclear power. Sounds like science fiction, right? Well, this isn't just a dream. It's the promise of nuclear fusion energy. It's the very process that powers our sun and stars, releasing colossal amounts of energy by fusing light atoms together. For decades, scientists have been working tirelessly to replicate this incredible process here on Earth. It's been called the holy grail of energy, incredibly difficult to achieve, but with world-changing potential. And after years of steady, often quiet progress, something remarkable is happening. Recent breakthroughs, both in major national labs and dynamic private companies, are generating unprecedented excitement. The dream of practical, grid-scale fusion energy feels closer now than it ever has before. So, in this video, we're going to explore the incredible world of fusion energy. We'll break down what it is, why it's been so challenging. Look at the incredible progress being made right now. Discuss when this potentially revolutionary energy source might finally arrive. Let's dive in. What exactly is nuclear fusion? Okay, let's start with the basics. You've probably heard of nuclear power before, often associated with nuclear fission, the process used in current nuclear reactors. Fission works by splitting heavy atoms, like uranium, into smaller ones, releasing energy. It's powerful, but it creates radioactive waste that needs careful long-term storage. Nuclear fusion is the opposite. Instead of splitting atoms, it combines light atoms, typically isotopes of hydrogen, like deuterium and tritium, under extreme heat and pressure. When these light nuclei are forced close enough, they overcome their natural electrical repulsion and fuse together, forming a heavier nucleus and releasing a massive burst of energy in the process. Think of it like this. It takes enormous energy to squeeze these positive nuclei together. But once they fuse, they settle into a lower energy state, and the extra energy is released as kinetic energy of the resulting particles. This is where the power comes from. The key fuels for fusion, deuterium and tritium, have huge advantages. Deuterium can be extracted from ordinary water. There are literally oceans of it. Tritium is rarer, but it can be bred within the fusion reactor itself from lithium, which is also relatively abundant. This means the fuel source is virtually limitless, available to everyone on Earth. And critically, fusion produces no long-lived radioactive waste like fission. The primary byproduct is inert helium, while the reactor components themselves become somewhat activated by neutrons during operation. This radioactivity is much lower and decays much faster than fission waste. Sounds perfect, right? So what's the catch? The huge challenges of replicating the sun. The catch is replicating the conditions inside the sun on a small scale here on Earth. It is incredibly difficult. To get hydrogen nuclei to fuse, you need to give them so much kinetic energy that they can overcome their natural repulsion and get close enough to let the strong nuclear force take over. This requires temperatures exceeding 100 million degrees Celsius. That is many times hotter than the core of the sun. At these temperatures, matter exists in a state called plasma, a superheated, ionized gas where electrons are stripped from their atoms. Challenge number 1. Asterisk. Asterisk. How do you contain something that hot? Asterisk. Asterisk. No physical material on Earth can withstand direct contact with 100 million degree plasma. Scientists have devised two main approaches to plasma confinement. 1. Magnetic confinement. This is the most common approach. Powerful magnetic fields are used to trap and control the plasma, preventing it from touching the reactor walls. The most studied design is the tokamak, a donut-shaped chamber where magnetic coils create a twisted field line configuration. Plasma particles spiral along these lines, effectively trapping them. Another design is the stellarator, which uses external magnets to create the twisted field lines in a more complex way. 2. Inertial confinement. This approach, often used in laser-based systems, involves hitting a tiny pellet of fusion fuel with extremely powerful lasers or particle beams from multiple directions simultaneously. This compresses the fuel to immense densities and heats it rapidly, causing it to fuse before it can fly apart due to its own inertia. Challenge number 2, achieving ignition and net energy gain. This means getting more energy out of the fusion reaction than you put in to heat and contain the plasma. For decades, experiments required more input energy than the fusion process produced. Breaking this barrier, reaching ignition, is a monumental task. Challenge number 3, materials, science, and engineering. The neutrons produced by the fusion reaction are highly energetic and bombard the reactor walls. Finding materials that can withstand this intense neutron flux and heat over long periods is a huge hurdle. Designing, building, and maintaining these complex machines is also an immense engineering feat. For a long time, fusion progress felt slow, incremental, and astronomically expensive, primarily confined to large, publicly funded research institutions. But that narrative is rapidly changing. The recent breakthroughs and the race to fusion suddenly, the fusion landscape is buzzing with activity and tangible progress. One of the most significant recent milestones happened at the National Ignition Facility in California, USA. NIF uses the inertial confinement approach, employing 192 powerful lasers aimed at a tiny fuel capsule. In December 2022, and successfully repeated since, NIF achieved fusion ignition, meaning they produced more energy from the fusion reaction than the energy delivered to the target. This was a monumental scientific achievement, proving the fundamental concept of inertial fusion ignition is possible. It's important to note that NIF is a research facility, not a power plant. The total energy required to fire those lasers is still far greater than the energy produced by the fusion reaction. But achieving ignition of the fuel itself is a critical scientific step forward. Perhaps even more exciting for the prospect of commercial fusion power is the rise of private companies. Fueled by billions in private investment, dozens of startups are pursuing a diverse range of innovative approaches. Often focusing on compact, potentially faster to-build reactor designs, companies like Commonwealth Fusion Systems, a spin-off from MIT, are developing smaller, high-field tokamaks using revolutionary high-temperature superconducting magnets. Their Spark project has already demonstrated the capability of these powerful magnets, paving the way for their planned net energy gain demonstration plant. Other companies like Helion Energy are pursuing different magnetic confinement concepts, aiming for direct energy conversion to electricity. TE Technologies is exploring field-reversed configuration plasmas. And there are many, many others, each with unique ideas and impressive engineering teams. These private ventures operate with a speed and agility, often difficult for large government projects. They are attracting top talent and substantial funding, creating a true race to develop practical fusion power. Meanwhile, the massive international ITER project in France continues to build the world's largest tokamak. ITER is designed to demonstrate the scientific and technological feasibility of fusion power on a large scale, aiming to produce 10 times more power than it consumes. For extended periods, though, it's not designed to generate electricity for the grid. It's a crucial but slower-moving step in proving the physics at scale. This combination of scientific breakthroughs at national labs and rapid innovation in the private sector is creating unprecedented momentum. The future, and when can we expect fusion power? With all this exciting progress, when can we expect fusion energy to power our homes and industries? The honest answer is, it's still challenging to say definitively, but timelines are accelerating compared to predictions from just a few years ago. Most experts agree that we are likely decades away from widespread, commercially available fusion power integrated into the grid. There are still significant engineering hurdles to overcome beyond just achieving net energy gain in a pulse. We need reactors that can operate continuously for long periods, are reliable, maintainable, and cost-effective to build and run. However, the optimism from the private sector is high. Some companies are targeting demonstration plants that produce net electricity within the next decade, possibly by the early to mid-2030s. These would be proof-of-concept facilities. Commercial pilot plants could potentially follow in the late 2030s or early 2040s. Widespread deployment and grid integration would naturally take longer, likely pushing significant impact into the 2040s and beyond. The potential benefits are so enormous: clean, abundant, globally accessible energy, that the investment and research continue to grow. Success in fusion would not only provide a sustainable energy source, but also open up new possibilities for desalination, industrial processes, and even deep space propulsion. The dream is getting brighter. Nuclear fusion has been a scientific dream for nearly a century. Pushing the boundaries of our understanding of physics and engineering, for a long time, it felt perpetually decades away. But the recent breakthroughs, fueled by both dedicated public research and dynamic private enterprise, have fundamentally changed the outlook. We've proven ignition is possible, and innovative designs are being rapidly developed and tested. The challenges remain significant, requiring continued ingenuity and investment. But the energy and optimism in the field are palpable. The dream of harnessing the power of the stars for clean, unlimited energy here on Earth is no longer just a distant hope. It's a future that scientists and engineers worldwide are actively building, piece by incredible piece. What do you think about the future of fusion energy? Could this really be the solution to our energy needs? Let us know in the comments below. If you found this video insightful, please give it a thumbs up. Don't forget to subscribe to Sciencepect for more deep dives into the latest breakthroughs in science, technology, and space. Thanks for watching, and we'll see you in the next video.